Welcome back to College Algebra. In this section we're going to be talking about rational functions. They're related to polynomial functions. You might be asking yourself why we're doing this here. Well, because we were just talking about polynomial functions. Well, it's just because they're related. In fact, the next couple of sections are going to be related topics before we go back to polynomials at the end of this chapter. So what is a rational function? Well, if you remember rational expressions from our review chapter, rational expression was just one polynomial over another. This is basically that. It's just a function equals that. So r of x is the division of two polynomial functions, is a rational function. And because it's based on polynomial functions, it has a lot of the same properties. Its domain would be negative infinity to infinity, like that of every polynomial function, except that we're dividing. So wherever the bottom is 0 can't be in our domain because it would be undefined there. So it's all real numbers except where the bottom is 0. Also, if you look at the graphs of these rational functions, the graphs of polynomial functions are continuous everywhere. They have no holes or breaks. Well, rational functions are continuous everywhere on their domain. So they might be continuous on all real numbers if their domain is all real numbers, but if their domain isn't all real numbers, they might be discontinuous at some different points. Zeros of a rational function always occur at the zeros of the numerator, because zeros of the denominator would make it undefined. Can't be in the domain at all. We're going to look at this f of x equal 1 over x because it's a good function to really illustrate most of the properties of rational functions. Let's look at f of x equal 1 over x. Make ourselves a point table. If you plug in with 0, you're undefined. You plug in 1, you get 1, 2, you get 1/2, 3, you get 1/3. So 1, 1, 2, 1/2, 3, 1/3. I feel like I may have already graphed this before in this class. Like when we were doing the end of chapter 3, like 3-4, I think I may have graphed it, but oh well. Let's get a little bit closer to 0. Because although I don't have a point at 0, I have a point close to 0. If you take 1 divided by 1/2, that'll just be 2. Because 1 over something just flips the fraction. 2 over 1 becomes 1 over 2. So yeah, 1/2 it'll be 2, 1/3 will be 3, etc. So it's going like this. Hugging closer and closer to the y-axis, and also doing the same thing with the x-axis. Because, as you get farther and farther out, like 100, it'll be 1 over 100. 1,000,000, it'll be 1 over 1,000,000. It'll get tiny, but it will never actually get negative. It just gets smaller and smaller positive. It will approach 0. And if you look at negative x values, like -1, -2, -3, -1/2, well, they'll be very similar. -1, -1/2, -1/3, -2. So, what am I doing? Down here. Down here. It's starting to get pretty late when I'm recording this. I'm getting a little tired. Glad this is my last video of the day. There we go. That's what the graph looks like. But note these lines. It hugs infinitely close to, but it does not cross, the x-axis and the y-axis. These are called asymptotes. This has a horizontal asymptote at y equals 0, the x-axis, and a vertical asymptote at x equals 0. An asymptote is just a line your graph approaches as it goes to infinity. So a horizontal line is a possibility. A vertical line is a possibility. We'll also see later you can even have slanted lines that maybe your graph might do, say, one of these babies too. So, could be vertical asymptotes, could be horizontal asymptotes, but they're very important because if you know asymptotes, you have basic guidelines for graphing your function because you know what it does as it goes off to infinity in every direction. So they're very important to find. In fact, they're probably the most important thing to find when you're analyzing and graphing these rational functions. So a big part of this section is going to involve how do we find these asymptotes. So, what I just said, here's the definition of an asymptote. Any line the graph approaches as it goes to infinity, really in any direction. Vertical asymptotes are the easiest to find. If you'll note, our vertical asymptote just occurred where our 1 over x was undefined. That's basically the idea. There's one refinement. You do need to simplify the function first. So if it reduces, you do need to do that first before you start pulling off the zeros of the denominator. So after you reduce the function, whatever zeros of the denominator are left, those are the asymptotes. Any ones that might have reduced away are still important, but those are empty points. We'll plot them, but they won't be asymptotes. We could also have horizontal or oblique, sometimes called slant asymptotes. They're slanted lines. And to find those, you need to know what the leading term of the numerator and the denominator are. And what kind of asymptote you have depends on the degree. So if you have the top degree is less than the bottom degree, like the one we started with, because when we looked at 1 over x, the top degree is 0, because that's 1x to the 0, and the bottom degree is 1. So top degree is less than the bottom degree. If that's the case, you always have a horizontal asymptote at the x-axis, at y equals 0. If they're equal, it's a little bit more complicated, but not much. There's still a horizontal asymptote, but it's at y equal a over b, the leading coefficients over each other. So if I, for example, had f of x equal 3x squared over 7x squared minus 2, they both have second degree polynomials. This would have a horizontal asymptote, HA, at y equals 3 over 7. Leading coefficients over each other. And remember, I mean, they're the terms with the highest powers. That's what you do if they have equal powers. You might expect the last case to be m greater than n. Well, it is, but it's more specific than that. If the top degree is 1 more than the bottom degree, it's a slanted asymptote. To actually find the formula of it, it's going to have to be a y equal mx plus b, because that's what the equation of a line looks like. To find it, you divide the numerator by the denominator. So those are both polynomials, so to divide them, we've got to do polynomial division. So either long division or synthetic division. Not the only time we're going to see long division in this chapter. But y equals the quotient, ignoring the remainder is the asymptote. So that'll actually save us some time on the division, because we won't have to calculate the remainder. We can just stop when we get the last term of the quotient. So where we're going to spend the rest of our time in this video is we're just going to work through all three of these cases. Then we're going to be done. So the first problem we're going to be looking at is problem 23 from section 5.3. we are going to start off by finding the domain. G of x squared minus 1 over x to the fourth minus 16. So find domain. All we really have to do that is figure out where the denominator equals 0. Then it's going to be all real numbers except those. So if I set x to the fourth minus 16 not equal 0, let's see here. Can factor that. X squared minus 4. X squared plus 4. Factor that. X squared minus x plus x minus 2. X to the 1 is 2x plus 2. X squared plus 4. So that'll be at 2 and negative 2. So all real numbers except 2 and negative 2. Set builder's notation would just be that. Not equal plus or minus 2. So that's our domain. Interval notation would just be negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Then the next thing we're going to do is we are going to see if anything reduces. So that's what the bottom factors to. Top does factor, but I don't think it factors to anything that would reduce. Get x plus 1, x minus 1. And on the bottom we have x minus 2, x plus 2, x squared plus 4. So yeah, nothing reduces. So let's talk about intercepts. X-intercepts for zeros occur where the numerator is 0, so that would be at negative 1 and positive 1. The y-intercept, just plug in x equals 0, so that would be 1 times negative 1 over negative 2 times positive 2 times 4. That's negative 1 over 16, negative 16. That's 1/16. Alright. Lastly, let's talk about asymptotes. Nothing reduced, so we have vertical asymptotes at the zeros of the denominator. Vertical asymptotes at x equal 2 and negative 2. Because x squared plus 4 can't equal 0, because you get imaginary numbers from it. And let's see, the top degree is 2, bottom degree is 4. That means the top degree is less than the bottom degree. M is less than n. So that means we have a horizontal asymptote at y equals 0. Alright then, let's draw some axes. As far as drawing the asymptotes, we have one at 2, so I suggest you do a dotted line for it, because it's not actually part of your graph, it's just a guideline. We have one at negative 2. Alright, and we also have an x-intercept at negative 1. And a positive 1. And we have a y-intercept at 1/16. That's interesting. That's very tiny. Very tiny. That's actually probably too high up, but I may change my scale once I get a look at what the graph looks like. So bring up the calculator. Now, note when you're plotting this in, almost on any calculator, you're going to have to tell it parentheses around the top and parentheses around the bottom. So, x squared minus 1 divided by x... Oh, see, I forgot them there. X to the 4th minus 16. So, I just want to look at the table, really. Calculate some values pretty quickly. Honestly, those are all pretty tiny values, so I don't think... I'm tempted to actually make my y's much tinier than that. I think I will. I will make, then, this distance 1. So this will be -1. But these will all go by 1s. So then 1/16, 0.06. That means this point will move there, from there to... This is 0.1, so 0.06 is about right here. And then 3 is a little over 0.1, it's 0.12. 4 is 0.06. And it looks like it's tending down towards the asymptote. So it's going like this. This. I presume as we get close to the vertical asymptote, so I'll plug in, we're going down, but we'll see. If I plug in, say, 1.5, get -1/10, a little over -1/10. So yeah, it's going down. It looks like it's a similar thing on the right, on the left side too. If we look at -1.5, yeah. And in fact, is it symmetric on the other side? It is. Okay. So that means, I suppose I could have told that, yeah, it's an even function. So here's what it's doing in the middle. And on the other edge. Oop, it does not cross, Paul. Alright, so there's a rough look at what it looks like. Using the same window I have there, I have -10 to 10 on my x's, but my y's I just made -1 to 1. So let's see how that looks on this thing. Yeah, more or less. The 83 has trouble dealing with asymptotes, so it tries to connect the ends, but you can kind of tell the look of it.